So, thank you everyone for joining for the very first lecture, FSML lecture for the semester. And it's my pleasure to have Dr. Panos Stinis. So Dr. Panos Stinis specializes in scientific computing with application interests in model reduction of complex systems, multiscale modeling, uncertainty quantification, and machine learning. He studied aeronautical engineering at the Technical University of Athens, Greece. He earned his PhD in applied mathematics in 2003 from Columbia University in New York and began his career as a postdoctoral fellow at Lawrence Berkeley National Lab and the Stanford Center for Turbulence Research. In 2008, he became a faculty member at the mathematics department at the University of Minnesota. He moved to the Pacific Northwest National Lab in 2014, where he is currently leading the computational mathematics group. So it's a pleasure to have you, Doctor, and without further ado, please take it away.
Yeah, thank you very much for the invitation. It's very nice to be here. So today I would like to mention a few topics that go here in the title. What can we do when big neural networks are not enough? And in particular, a collection of ideas that have been developed at Pacific Northwest National Lab over the last few years that center around the concepts of physics, multifidelity, and kernels. And I have to say that this is primarily the work of the people that I list here: Amanda Howard, Wenxian Chen, and Saad Kadir. And I'm here to basically present this. And this is work that has been funded over the last several years, both externally by the Department of Energy, but also internally at PNNL. So let me start with a statement of the problem. So modern machine learning has shown remarkable promise in multiple applications. However, as we have all also witnessed, brute force use of neural networks, even when they have huge numbers of trainable parameters, can fail to provide highly accurate predictions for problems in the physical sciences. So what we think needs to be done is that we have to have methods that exploit domain knowledge, but also architectures more effectively. And the idea of this presentation is to show some ways of exploiting domain knowledge, but also architectures more effectively. So let me start with the simple talk outline. The first concept that is in the title is that of physics. And as far as physics is concerned, what I want to present is an approach that uses machine learning-based spectral methods for partial differential equations. Then when it comes to multifidelity, we have developed several frameworks, I would say. One is what we call the serial, and I will explain where the name serial comes from. And it's a multi-fidelity framework, in particular for deep operator networks. And then we have another framework, which we call the parallel or feature-adjacent multi-fidelity learning, and I will provide more details about this in a few minutes. Then there is another idea where one can take physics-informed networks, which are very popular for computing solutions of, let's say, partial differential equations, and one can stack those so that without going to large architectures, one can gain the benefits of having higher accuracy. And then one can also have stacking networks with domain decomposition. I don't know if I will have time to cover all of this, but I will try to give at least some hint about how they work. And the last topic, which has to do with kernels, is that one can go back to the theory of kernels as surrogates for neural networks. And in particular, we have used those to do both improved regression, and this has to do with physics-informed deep operator networks for partial differential equations, but also classification, and in particular, how to fine-tune large language models. And hopefully we will have time for the last bullet here, which says a broader framework, that all these things that I will be presenting are part of a larger framework that extends through different topics in applied math, but also pure math and computer science. So let me start first with the physics, and in particular this topic of machine learning-based spectral methods. And if you are not familiar with what spectral methods do, the basic idea is that many years ago, a couple of centuries ago, very clever mathematicians came up with sets of orthonormal functions. And these are now famous families of orthogonal polynomials like Legendre polynomials, Fourier bases, Hermite polynomials, etc. And the idea is that one can take the solution of, let's say, a partial differential equation and expand it as a linear combination of these orthonormal basis functions, and then plug it into the equation and derive into the partial differential equations and derive algebraic equations or ordinary differential equations for these coefficients, a, k here, and that leads to an accurate and efficient numerical procedure under some regularity assumptions. This is one of the really very powerful methods in traditional scientific computing. However, there is one important point, which is that one has to come up with good basis functions, with good representational capability, and this is non-trivial. So the idea, what we would like to do here is to use machine learning to get such functions just from, just use machine learning to get these functions. So how would we go about doing something like that? We want to start by extracting these candidate basis functions from the framework which is known as deep operator networks, or DeepONet. And this framework, which is based on the universal approximation theorem of operators, says the following, that back in 1995, which is now 30 years ago, Chen and Chen proved this nice theorem that if one has an operator G script here, then one can find a network B and the network tau, which later were called branch and trunknet, so that if one takes a dot product of the output of the branch and the trunknet, then it can approximate the action of the operator on any input function V and evaluate it at any query point Y to within any required tolerance, okay? So that was for one hidden layer networks, that the theorem was about, but in 2021, this was generalized to replacing the trunk and branch nets by deeper networks to make them more expressive and computationally feasible, and that gave rise to DeepONets, which are one of the popular operator networks. What I will present here can be used, I will be talking about DeepONets, but the same ideas can be applied also to other operator networks, like, for example, Fourier neural operators. So let me start by why we would like, first of all, to do that. If we start with DeepONets can be very good at training for interpolation. So if we take, for example, a simple advection equation here in 1D in the interval 0 to 1, and we train it, let's say, with data from time 0 to 1, as you see here, if I plot the relative error as a function of time for interpolation, so time 0 to 1 only, then as I increase the number of training epochs, I can get the error to be pretty decent here. However, the moment I try to do extrapolation in time, and I go beyond time 1 to 2, 4, 6, 8, etc., you see that the error grows very fast, and the relative error grows very fast. So then this means that the extrapolation ability of the DeepONets is not very good. However, what I want to talk about today is that we can build on what DeepONets do to extract basis functions that will allow us to really train within a limited time interval and then be able to extrapolate very accurately for times well beyond the training interval. So how would we go about doing something like that? As I mentioned before, in the DeepONet, there are two networks. There is a branch net and the trunk net. And if we go back here to the way that the universal approximation theorem for operator works, we see that the output of the DeepONet is a dot product of the trunknet functions with the branchnet function. So one can think of that as a linear combination of the trunknet functions. So in this way, the trunknet output functions can be thought of as candidates for those basis functions that I will try to use to construct real basis functions. And so the question is, how can we take this tau k and then build them into a hierarchical orthonormal basis? So this is the task that we have to do. And there is an obvious way that one can try to do that, which is by taking, for example, the same thing that people do in POD. We can take the trunknet functions and we can evaluate them at the quadrature points, and then we can form this matrix A, IK, and then we can compute the covariance matrix here, and we can work with that. However, as you can see quickly, if n sub q is the number of points that we have in this quadrature, the matrix that we have to work with is n sub q cross n sub q, and this is prohibitive as nq scales with the dimension. So instead, we say, okay, we're not going to do that. Let's see what else we can do. Instead, we can define this matrix script A, which comes from the evaluation of the inner product of tk here with some function g, for example, when it acts on it, and we can work with either a script A star or with the adjoint of that. The nice thing about this is that the moment you go to this adjoint formulation, instead of having this huge dimensionality, you only have dimensionality p cross p, where p is the dimension of the output of the trunknets. In other words, how many trunknet functions you have. And in even more than that, you can find this very nice change of basis that goes from the tau k, which the DeepONet provides us with, to these new orthonormal basis functions U sub L. Okay? So we are happy. We were happy because we said, nice, we'll just take the trunknet functions, we plug them in this relation, we get the U sub L. And then we try to apply this to something very simple, which is here, for example, you can see what these first two basis functions look like. Indeed, when we do this, the singular value decomposition, we get this very nice singular value decay, all right? And then we try to apply by projecting a very smooth function like e to the sine 2 pi x on these acquired orthonormal basis functions u sub k, and we find something that is very worrisome. In particular, what we see is that the projection coefficients, while initially they decay exponentially, at some point they stop decaying, and then they start growing up, and in fact, they become order 1. So this is not good at all. And then there is a simple explanation why this happens, because if we go back to this expression that we were using, we see that here we divide by the singular value. And by seeing here the singular value decay, we have a lot of singular values that are close to machine precision, which then, when you invert them, they give you lots of round of error. So we need to avoid this altogether. However, there is another way that we can do things, which is well-conditioned. And in particular, if we go back here, and instead of working with the whole matrix A star, we only use the matrix A multiplied by the square root of the matrix of the quadrature weights, we find that, and when we perform a singular value decomposition on this matrix, we can recover the values of these unknown orthonormal basis functions on the quadrature grid. This is extremely important because when we want to actually perform a projection, the important thing is to have accurate values of those unknown basis functions on the quadrature points. So by having this, we are able to get a new basis functions which are well conditioned and they don't suffer from this problem. However, there is one more thing, that this singular value decomposition allows you to get the values only on the quadrature grid. So what happens for the values away from the quadrature grid? Here you will have to rely on some extra projection. For example, you can do in one dimension Legendre polynomials. The nice thing is that you don't need to use a lot of them because the functions that you're working with are already smooth. And indeed, if we apply this to, for example, the e to the sine 2 pi x that we had tried before, we see this very nice now decay of the projection coefficients, which is exactly what one would expect if we have genuinely orthonormal basis functions, where we have exponential decay with the index of the basis functions, and then indeed the projection coefficients became very small and stayed there. So in this way, now we have this u tilde L that we are going to use as basis functions to solve partial differential equations. And that's how we power a spectral method. Given a PDE, we train a DeepONet, we extract the hierarchical spatial basis built out of the trunknet functions, and then we use that to power a spectral method and compute the solutions. So how would you do that? You take the linear combination of those new basis functions, and you follow the usual Galerkin procedure, and you apply it to the partial differential equation that you are interested in, and you obtain a system for the coefficients, which then you solve, and you get the solution. Okay, so let me just show you some numerical results. First of all, for the advection equation, if you remember, when we only used the DeepONet, we trained from time 0 to 1, and then the moment we went out of that interval, the relative error, which I plot here, became quickly close to 75 to 100%. While here, as you see, both in distribution and out of distribution, we are able to keep the relative error at very, very low values, okay? So this is, and not only for time 0 to 1, but way beyond the training interval. So this is just for the advection equation. Now, for the Viscus-Berger's equation, we can also get a very small relative error, both in and out of distribution and for long times. Similarly, for the KdV equation, we can get way beyond the training interval, very good small relative error in and out of distribution, and similarly for the Kuramoto-Shibasinski equation in the chaotic regime. So I know this must have been fast. This is a pretty long paper, but if you have any questions, you can ask me now or later, and I'll be happy to provide more details. So let me move to the next topic, which has to do with multifidelity. And the first is what I mentioned before, the serial multifidelity framework. In particular, we assume that we have the following construction that you see here. We have something which we call the low fidelity block, which could be a low fidelity numerical solver. It could be a low resolution solver. It could be just a low order model, a physical model. And then we have we make a prediction based on this low fidelity block, which is then fed into two blocks which are going to produce the corrections. There is the linear correlation and the nonlinear correlation, which are then added up, and one gets the high fidelity approximation. So in other words, the linear and nonlinear correlation networks take the information that is in the output of the low fidelity block and add to it or transform it whatever is needed to become a high fidelity approximation. And the details for that can be found in this paper, but let me give you an example about a highly non-trivial problem. this is for the case when we use operator networks, but the important is not necessarily what you see here, but let's see an example from a non-trivial problem, which has to do with how to predict the evolution of ice sheets. And in particular, what we want to do is we want to train an operator which will take as input the topography that is under the ice sheet and the height of the ice sheet, and it will output the velocity of the ice sheet, which in our case, it's a two-dimensional problem. So we have v sub x and v sub y for the two components of the velocity. Beta is the topography and capital H is the height. So beta and capital H are going to be the input of an operator that we want to train, and v sub x and v sub y will be the output. And here we assume that we have data from multiple resolutions. We have a coarse resolution, which you see on the top row, and high resolution that we see on the bottom row. So let's see how we can apply this framework to get predictions for the two components of the velocity. The first thing that we can do is what we call single fidelity. So we use a highly accurate finite element solver, and we use 10 samples. So we sample 10 times the beta, which is the topography, and for each one, we solve through this finite element method to compute u and v, and that's what we call the single fidelity, okay? And we find that it's actually not good in the sense that the relative error that we get when we train a single fidelity operator is actually close to 70%. This is really not good. Now, if we take this single fidelity operator and we pay even more computational price by going to 50 high fidelity samples that are used for the training, we can indeed do much better, and we can bring the relative error down to 5%. However, we had to produce 40 more high fidelity samples, which can be expensive. So what we did, on the other hand, with the multi-fidelity, we said, okay, we will only use 10 high fidelity samples, not 50, and then we will use a lot of low fidelity samples, in our particular case, from a much lower resolution. So the high resolution was 41 squared, the low resolution was 15 squared. And when we do that and we combine them in this serial manner, we see that we are actually able to obtain a result that is comparable to what was in the single fidelity with the 50 high fidelity samples. So this is just an example that indeed multi-fidelity can help in different cases, even for demanding problems like this one. Okay, that was the serial framework, but there is also something that we call the parallel multi-fidelity framework, and this was developed by Wenqian Chen, who is a postdoc at PNNL. So Wenqian Chen at the beginning wanted to work, he tried to work with the serial framework, and he didn't like it, so he came up with his own version of multi-fidelity, which is the parallel. So why do we call this the parallel? Let's look at this figure to see what is different between the previous framework and this one. Here in the parallel framework, one takes both the low fidelity input and the high fidelity input and puts them through an encoder, this encoder net, into a common feature space. And then in this common feature space, you have the low fidelity features, which are in green here, and the high fidelity features, which are in blue, and one needs to find what is the correlation between them, but we do so in this common feature space. And how do we find this correlation? In particular, we say that the high fidelity features are the low fidelity features plus a small trainable correction. The trainable correction is exactly this vector lambda that you see here, and that's what you train to find the connection and correlation between low fidelity and high fidelity features. After that, you have a common decoder net, and each one of the two projections goes into its own loss function. So you have the low fidelity loss function and the high fidelity loss function. So this is why it's called parallel, because we process in parallel the low and the high fidelity information that we have. Again, this information can be all sorts of things. It can be data, it can be physics, it can be only physics or only data, or mixture of physics and data. So let's see such a mixture of using low fidelity data and high fidelity physics for a difficult problem, which is the steady lead driven flow. This is a 2D problem. And as you may have seen in the literature, if one tries to use, for example, a low fidelity numerical solver, as you see that this is the red line that you see here, and I plot the relative error as a function of the Reynolds number. And you see that it does equally poor for across Reynolds numbers. Now, if we go to a single high fidelity solver that uses only physics, that would be a PIN, a physics-informed neural network. This one performs very nicely for low fidelity, for low Reynolds number, but as the Reynolds number grows, then the error can quickly grow too. So what we would like to do is we would like to take this red, which is the low fidelity numerical solver, with this blue, which is the high fidelity physics only based neural network, and combine them through this parallel multi-fidelity framework. And we did that, and we get the black, which is the MF here, the multi-fidelity, which, as you can see, across the Reynolds numbers, produces a relative error, which is actually, until the moment when we published that paper, it was the best that could be found in the literature. I don't know if this has been substantially improved. And then there is also the green that you see here, which is what happens if you have both high fidelity physics and high fidelity data. That would be somehow the best that one can do. So we see that with the multi-fidelity, which uses only low fidelity data, we can still get pretty close to what would be the optimal. Okay, now let me say a few things about this idea of stacking physics-informed neural networks. So the main idea is that one can train a pin on the same domain multiple times. But what does this mean? You can train a single fidelity pin, and then you can consider that this single fidelity pin is a low fidelity approximation of itself, in a sense, so that you can take the output, like here, as I'm showing, of the pin, and you can feed it in a multi-fidelity framework that then uses, again, the loss function, which is based on the PDE, which is another pin, to improve the first pin prediction. And this you can do repeatedly. So here I have, and you can have this, that's why we call it a stacking physics-informed neural network, because you stack pins with corrections on top of these pins, which are also trained with the residuals of the physics. That's why they are in the same idea of physics-informed neural networks. So let's see a simple example here, actually simple in the sense that people have used other methods to solve it, but here we will just take a vanilla pin, no special tricks about it, and we will just use this stacking approach to improve it. So what I have plotted here is the relative error for this wave equation in 1D, where, and the iteration that we see here on the horizontal is the number of stacking iterations. So 0 is the original vanilla pin, okay? And then we see that as we keep doing this iteration, we start bringing down quickly the error with a few iterations. And of course, you see that there is some kind of saturation here that happens. This is expected for two reasons. One reason is that if you do this stacking multiple times, you will eventually resolve all the small scale activity that could be resolved. That's one case. The other case is that even if you do the stacking at some point, you may run out of resolution, in a sense that the neural networks that you use can only have a finite resolution. So you may have to use a larger network. But even with a simple vanilla pin architecture without going to a large network, with this stacking approach, one can improve significantly the accuracy of the prediction. So this is just with physics. There is no data used here. And this can also be extended to the case of physics-informed operator networks. In particular, here, we tried on a problem that in terms of physics-informed operator networks has proven to be very difficult to do. And that's the problem of having the viscous Berger's equation with this particular value of the viscosity, which is 10 to the minus 4, which is the value of the viscosity that seems to be like a wall that everyone hits when they try to do physics-informed operator networks. So what is the best that one could do? Whenever you have physics-informed operator networks, because in the loss function you have multiple terms that appear there, one needs to weigh them appropriately. And the neural tangent kernel weighting has become one of the best ways of weighting actually these different terms. So the best result that existed in the literature was this orange that you see here, which says NTK and fixed. And let me explain what fixed means, okay? So in the literature for a single fidelity, which is iteration 0, the best that one can do would be this point here. So when we used our construction and we started and we used the NTK to do the weighting and we do this stacking iteration, we couldn't make things improve, right? So we could only stay within what was the state of the art. However, Amanda Howard had a nice idea that one doesn't have to keep the viscosity fixed for all the iterations. In fact, in a way that is similar to simulated annealing, one can start with larger viscosity in the first iterations and then start lowering the viscosity as the iterations progress. And by doing that, that would be this light blue curve that you see here, that within a few iterations, we were able to get a relative error which was half of what was the state of the art last year when this work appeared. So there is a lot more work to do in this domain about physics-informed operator networks, but this idea that you can start training with an easier problem and you can slowly go towards the original problem, which was more difficult, I think that this is a promising idea that can be applied in other contexts too. Okay, so last topic and is how we can use efficient kernel surrogates. And in particular, I will talk here only about regression. I will not talk about classification, but let me go back to give a one-page summary of what kernel methods do. So kernel methods, based example on the neural tangent kernel, can be used to study theoretically the infinite width limit of neural networks. So this is something that has been well documented. And in fact, there is theoretical justification too. However, there is also numerical evidence which suggests that kernel methods can find surrogates for finite width neural networks, okay? However, the important thing is that such kernel surrogates need to be efficient, because if you just do the simple neural tangent kernel for a huge but not infinitely wide neural network, it's still prohibitively expensive. And let me explain what is that. So if you have not heard about the neural tangent kernel, the neural tangent kernel comes about by taking the output of the neural network and differentiating this output with respect to the parameters of the network. So you form this feature map, and then you take the product of this with its transpose, and you make this neural tangent kernel matrix version. So go and imagine what would happen if this theta here is the number of parameters of your network. That's the cardinality, right? If you have a very large network, like the networks that people use nowadays, this is just impossible to do, right? If the cardinality of theta is in the billions or in the trillions, you cannot form this matrix and hope to work with it, in any efficient way. So what we proposed is that what if instead of using this neural tangent kernel, which uses the derivative with respect to all the parameters of the network, we focus only on what we call the conjugate kernel, which uses a feature map which involves only the parameters of the output of the network with respect to only the last layer. So these are the WKs, which are the weights, and these are the Bs, which are the biases. So if we look at it in the matrix form, then the NTK is, of course, the CK plus the rest of this stuff, right, which goes into this matrix E. So what we would like to find out is if there are conditions under which we can ignore this E, okay, and we get something that is now, even for huge networks, if we only use the conjugate kernel, is something that is actually doable. So indeed, there are conditions under which one can use the CK, the conjugate kernel, instead of the NTK. And in fact, one can prove a couple of theorems here that the error that one commits in approximating a function f by using only the conjugate kernel can be bounded from below and from above from the error that one commits when using the whole NTK. So this depends on the regularity of the output of the neural network. And so the nice thing is that the cost of computing the conjugate kernel at a pair of points is the same as that of evaluating the neural network at those points. And of course, it is much cheaper than the evaluation of the NTK. So how can one use this? Here, I will only say how to use it in regression, even though I also mentioned that one can use it, for example, to accelerate fine-tuning of large language models for classification. But let's see how we can use it for regression. As I mentioned before, a couple of slides before, when I talked about physics-informed operator networks, a very important aspect when one tries to train a physics-informed operator network is how to weigh the different terms that appear in the loss function. So the neural tangent kernel, as I mentioned, has become one of the best ways of doing that, but it is very expensive, okay? So what we did here is we said, can we use the conjugate kernel instead of the neural tangent kernel to do the appropriate weighting for the different terms in the loss function? And indeed, it turns out that for the same problem of Berger's, which I mentioned before, we can do that. And here I have in this table, what is the error that one commits for different values of the viscosity. And we see that when one uses the NTK weights or the CK weights, the results are pretty comparable. But the nice thing is that one can do that by using the CK weights, which cuts basically about 60% of the time that you would need to do the training if you use the NTK weights. So indeed, using the conjugate kernel weights can actually help you maintain the accuracy while at the same time increasing significantly the efficiency of your training. So this is one example here, which is from the Berger's equation, and I'm using that because I had the same example a few slides back. Okay, so last slide, and I will stop for questions. This broader framework that I promised in the outline is the following. If you look at what we have been doing, many times a lot of these methods, what they do is that I presented is that we start with something like a simple solution, and by feeding it through some layer where it gets improved, we are basically using this concept of composition to try to improve the approximation that we do, okay? So this notion of compositionality, of course, is at the core of deep learning itself, right? Where we have the layer composition. ResNets are exactly this, right? That you can have, through composition, you can get small corrections as you go through the layers. And of course, the ultimate version of that is the deep equilibrium models if you assume that your number of layers really go to infinity. I'm not talking here about neural ODEs, but something else. Now, if we go to stochastic processes, there is a similar approach that one can construct a good basis to expand the solution of the stochastic processes. And in particular, if you look at this concept of rough path theory, these bases are computing through iterated integrals, which compose basically the basis functions as you go to higher and higher. And that's how you get good representation. So it's the same concept here of compositionality. If you go to numerical methods, there is indeed, in particular, Runge-Kutta methods. Runge-Kutta methods are also based on this composition of stages that you have. And there is an underlying group structure, which is called the Butcher group, and the iterated Butcher series that share a lot of common features with the iterated integrals that are used here in rough path theory. If you go to physics, and in particular in high-energy physics, you have this concept of perturbative renormalization, which is based on the operator product expansion. And there is the concept of Chen's iterated integral, which is similar to this iterated Butcher series and the iterated integral. So you still get, again, the same compositionality. If you go to computer science and in computability theory, there was this very nice work that appeared about 15 years ago by Yuri Manin, which said that there is analogy between the concept of energy in physics and the concept of complexity in computability theory, and that allows you to renormalize potentially non-halting problems. And if you go and you look into the details, you have similar constructions that are based on this compositionality, which allow you to get these higher order terms in the renormalization that you do for these non-halting problems. And going back to work that I was involved myself for several years, if you look at complex systems, you can make another analogy between high energy and between energy and complexity and the smoothness of initial conditions, and that can allow you to renormalize potentially singular solutions. And there is, again, a concept of compositionality that appears in the constructions that you have to put in place. Of course, there are a lot more in this area, but I'm hoping that this discovery of this common concept that lies underneath can help not only traditional scientific computing, but also find new ways to interact with deep learning and other topics also here in math, physics, and computer science. So thank you very much, and I'll be very happy to take questions. And if you also have questions, comments, please reach out through email. Thank you.
Thank you. That was a very, very interesting talk.
Thank you.
We can take this. Yeah, open the floor for questions in the room, and then maybe we can move online. So, yeah.
Yeah, thank you for the great talk. I have a question in relation to what you showed on slide 23, and it was the flexible, I think, viscosity that you were doing.
Yes.
In your framework. So how do you determine, like what rate to decrease that viscosity at?
That's a great question. Yeah, that's a great question. So the answer is you don't stay too long and you don't do it too quickly. So not too fast, not too slow. We found out that if you try to do it too fast, the system doesn't have time to, let's say, train even moderately in one viscosity, and you kick it to try to find the solution to another viscosity. On the other hand, if you stay too long and you train a lot, and you do slowly through the iterations, the decrease of the viscosity, then it gets stuck to local solutions and it cannot jump. So I admit it's an open problem. We don't have a good answer to it, but with simple experimentation that we did for this problem, we were able to actually get the results that you see here. We also tried it for the wave equation, where we tried to make the velocity high, which is very difficult to train physics-informed neural networks, and we were able to get it there too by starting from a wave equation with a low velocity and slowly increasing that velocity. But it's a very good question. Thank you.
Yeah, thank you.
Any other questions?
I have a question on the feature adjacent multifidelity
Yep.
framework. So you said there are going to be common features between the low fidelity and high fidelity features?
Well, it's a common feature space, and what changes is you can think that in this feature space you have some kind of an expansion of the solution, and what changes is the coefficients in front of this expansion. So you can think of it also in some kind of a model reduction perspective, where you have the full order model and the reduced order model. They can be expressed from the same basis, but with different coefficients in front.
I see. Following, but so is the encoder net and the decoder net same for both of these fidelities?
Yes, yes. So you bring them into a common latent space if you want. This feature space is like a latent space.
I see. Thank you.
Yeah, yeah. Yeah, and we have tried different encoders. We have tried, linear, non-linear encoders. Also, we have tried putting in here before the encoder maybe some Fourier features, things like that. But the important thing is that they go into a common feature space. That's the important thing.
I have a question.
Yep.
Since you train on the same parameter space, were you had to use the same number of high fidelity samples as low fidelity? Did you just observe better performance by using this framework, or did you just start with high fidelity samples or something like that?
Because each one goes into its own loss function, we don't need to have the same number of samples. So if you look at the paper and you look at the loss functions where for the low fidelity output and the high fidelity output, they can have different number of points that we evaluate this, that go into the loss function estimation. If that was your question, I don't know if you meant something else.
Yeah, so essentially you'd still require less number of high fidelity samples, right?
Oh, yes. I mean, hopefully the hope is that you will not have to use a lot of them, right? Yes. In that particular example where I showed, because we use for the high fidelity just physics, we didn't have access to high fidelity data. We only used as many collocation points as we wanted or as we needed. So, but if you have data, the hope is, yes, that you will use less high fidelity data.
I see.
Yeah.
Thank you.
Yeah. The original, I want to make a comment here, both for this and for the other framework, is that we want to go to regimes that right now are non-reachable. So, for example, imagine that you take the best direct numerical simulation that you have, which, however, is not for fluid flows, right? Which, however, cannot go to very large Reynolds numbers. But what if you consider this as a low fidelity, and then you use physics to correct it, right, on top of that? So that's what is the goal that we have with this kind of construction, to be able to go to regimes where either one doesn't have data, good data to train with, or where one has good physics that have not been used yet.
Thanks.
Yeah, yeah.
I had a question about the stacked pins framework.
Yes.
So I was wondering that if you are now doing this sort of stacking, each individual pin that you train at the different iterations, can it then be smaller compared to the vanilla pin approach, or then would you still have?
Exactly. Thank you for this question. This was exactly the reason why we did that, because we found out that these pins after the first one can actually be much, much smaller. So overall, if you take all the trainable parameters that are in this stacked construction, they could be, half of what you would need if you wanted to have a single fidelity pin and get the same result. So indeed, yes, that's the nice thing about multi-fidelity, that at every step you learn only what has not been learned so far, and that you can do that with a smaller network. And that's why overall you get a construction which has a lot fewer trainable parameters. Of course, I have to say that there is a price that you have to pay when you evaluate things. You have to start at the beginning, at the level 0, and then move, pass the new input through the whole construction. But because it is a smaller network, it's also much faster to evaluate.
Understood.
Yeah.
Yeah. Thank you. Makes sense.
Yeah, I have a question on the learning of the hierarchical basis sets, where then you can go to the essentially this long time scale. So my question was that if one were to use a brute force spectral basis, how? But is the number of basis dimensionality of the basis functions reducing compared to?
Yes. A great question. So we have found that, of course, here we set ourselves up with a very difficult problem, because for periodic boundary conditions, you have Fourier bases which are the best, and when we tried Dirichlet boundary conditions, you have Legendre polynomials which are the best. So there is no way that we can use fewer, but we have found that we can use a comparable number of basis functions. But the hope for that we are working on right now is not to solve one-dimensional problems where you do have already, the best candidates, but we want to go to higher dimensional problems and more difficult geometries where there are no natural candidates for basis functions to use for spectral methods. So yes, this is and what we have found, which is a paper that only appeared a few months ago, is that here we did data-driven, but if one does physics-informed DeepONet, because you enforce the physics during the training, you can get somehow better basis functions, so they're more expressive, and as a result, you can end up needing fewer of them than you would do if you only use data-driven DeepONets.
I see. Thank you so much for the explanation.
Yeah.
I have a question to follow up on this, and I think it's about 3 slides before this. This was your way of being able to represent your learned. I think one more before this. Yeah. So here, to evaluate off of the grid, you're projecting them onto Legendre polynomials in this case.
Yes.
How many Legendre polynomials do you need to use to be able to project on this, and does that have a huge impact?
Yes. Here we used in this particular one, we used 127. Because we wanted to go all the way down deep into the regime here where you are, at a very small value of if you see here, the projection coefficient is 10 to the minus 12. But you can stop somewhere here at 40, right? You would still get a nice representation. So you don't have to use a lot. And the reason for that is that the functions that you're trying to approximate with Legendre polynomials are already smooth. Let me give you an example. These are, for example, the basis function. That's what they look like. All right. So they're not terrible functions. Of course, I have to say that this depends a lot on the activation function that you use for the trunk net. These are with hyperbolic tangent. If you use ReLU, the basis functions can turn out to be much more jagged. So you have to be careful there.
Okay. That makes absolute.
And to add on to your question, the question that actually bothers me is what happens when you go to higher dimensions, because you don't want just to do tensor products of Legendre polynomials, right? So you want to have better bases, but there are, and what happens if you go to domains that are not simple, like not a simple square or a rectangle, what do you do there? So we have some, we're experimenting with some ways that use some kind of least square approximations of basis functions that you can basically take a complex domain and you can embed it in a more regular domain, and you can use restrictions of basis functions from the more regular domain. So that would be the real test for this construction.
Okay, that makes sense. And this may tie back to the question that was just previously asked. Did you do a comparison of just using 127 Legendre polynomials to
Yes.
this one that you fit right there? And comparable accuracy is what you're saying in those cases?
Yes. Everything that you see here is, for example, all the relative errors are with respect to Fourier, which are the best. And we
Okay.
have in the paper comparisons with Legendre polynomials for the case of Dirichlet boundary conditions. The very interesting thing that we found, which we haven't had time to explore, is that if I take the basis functions that were trained with periodic boundary conditions and I use them to solve a problem with Dirichlet boundary conditions, we still get a very decent results. So this means that these basis functions learn something fundamental about the operator itself that can accommodate different boundary conditions. But this is just for 1D, right? I'm not making any broad claims about, higher dimensions.
Okay, perfect.
Yeah.
Thank you. I'll let other people ask questions. I got more stuff on later ones, but I'll let other people jump in on some
Yeah,
questions.
sure.
I have one question maybe. So for the viscous boundary equation, the error with time first increases and then decreases. It is kind of surprising. So how is it able to self-correct itself?
Say it again, the last part.
Oh, sorry. So usually I mean, I haven't worked on these things, but usually I would expect that error to increase with time. But here,
for Berger's, it's actually expected, because what happens is that as the time progresses, initially the gradients steepen, so that you get an increase in the error until the viscosity starts taking over, and then the error starts decreasing, right? Because then the nonlinearity is no longer strong enough. So then it becomes mostly like a diffusion equation.
Oh, I see. Okay, thank you.
Yes. So while for the other ones, KdV, as you see here, and Kuramoto-Siwaczynski, indeed, it increases, because for KdV, you have the interaction among the solitons that if you don't get it accurately, the error starts compounding. And for Kuramoto-Siwaczynski, it is expected to increase because we are solving here in the chaotic regime. So the error keeps compounding with time.
Thank you.
Yeah.
Any other questions, like either in the room or online?
Yeah, I'll take the last little bit if there's nothing else out in there. This was on page 17 for some of your low fidelity and high fidelity models in these cases. Questions for two of these was, what is the computation cost in this example here? Do you know between the low fidelity and high fidelity? And have you guys checked to see, is there some optimal for a computation cost of how much cost you can allocate to these problems of what should be used for high fidelity and low fidelity, and what gives you the most accuracy in these cases? So a cost accuracy balance of how many of each the samples.
I don't remember how much cheaper was the cheap one, but because it is 2D, I mean, as you can see here, as you decrease the resolution, things can improve quadratically in terms of cost. But I don't remember how much cheaper it was. But overall, adding 100 of those low fidelity solutions really was not. It didn't make a lot. It didn't require a lot of computational time. So overall, the multi-fidelity was cheaper than doing the 50 high fidelity computations. Okay. But this is a great question. What you're asking, how much you can get away with, right? Here we got away with using only 10 instead of 50. But can we go to 5 and still get something reasonable? We haven't tried that.
Okay, great. Thank you.
Yeah.
I had one more question on this as well. So there are like other operator networks out there that like claim that they can do super resolution, right? But with the same test error as on the resolution it's trained at. How does something like that compare against your model? Because they say that they claim that they don't require a true high fidelity simulation to get a same error rate when you do like a finer resolution simulation.
when you say about super resolution, you mean that you train in a certain resolution and then you can get results for high resolution?
Yeah, I mean that is, I guess, similar to the multi-fidelity approach here, right? I mean the
Yes,
fidelity is coming in through the resolution. Yeah.
right. But there is no guarantee, right, that if you train with a certain resolution, you will be able to produce results at a much higher resolution. So we have, you can try that. You have to pay some price to get high resolution data. So that was our, experience. So the question was, how much more high fidelity data do we need? Can we get away with a little bit only? So instead of thinking of having 10 high fidelity and then adding 100 low fidelity, go the other way around. Suppose that you have 100 low fidelity and you ask yourself, how much should I pay for these expensive computations to get good high fidelity data? And it turns out that you can get away with relatively few.
Yeah, I agree.
Yeah.
This definitely does make sense. I was just curious because I've seen like work out there that claims that even if you train on like a particular resolution and you get like a certain test error, even if you can show you can they demonstrate like super resolution with a similar test error without training on any high fidelity samples.
I don't really believe those claims. I think that you can get this kind of super resolution if the resolution that you use for your training is already enough to cover all the small scale features. Otherwise, we would be training with whatever data is available now, and we would be able to go into much, much smaller scales, which to me, it looks like you're creating information out of nothing, really.
I agree. I was just wondering if you like compared to
Yeah, for me, it looks like an extraordinary claim that we can use a fixed resolution and you can always get equally good predictions for much smaller resolutions. There is some information there in the smaller scales that you never put into your training. So really, where does all this knowledge, new information come from? The only way that we found, for example, is that if for the spectral method stuff, right, that when we train with a certain resolution, but we bring back the physics through the spectral method, then yes, we are able to get better results for longer times, but not without paying some price.
Cool. Thank you.
Yeah.
Any other questions? If not, let's just thank the speaker one more time.
Thank you very much. That was very nice, and thank you for all the very good questions.
Thank you for this very, very interesting talk. Yeah, we all sure learned a lot.
Yep. And if you have more questions, please feel free to send me an email.
Sure.
Yeah.
Right.
Thank you.
Thank you again for giving this talk, and see you guys later.
Thank you. Have a nice day.